Bismillahirrahmanirrahim. I am Usman Javed and this is a determinate structure analysis class. In this lecture we will discuss about the cables. Cables are basically the structural elements which takes the loads. The cables are used in different applications. They are used in high tension wires, high tension voltage wires for transmission of electricity. These cables are also used for load carrying capacity. Like they can be used in bridges. They can be used in pre-stressing of girders and etc. So in this lecture we will discuss the cables as a load carrying objects which takes the loads of different structures. So the content is introduction to the cables, cable subjected to concentrated loading, and the cable subjected to the UDL, uniformly distributed loads. So cables are purely tension members. They only take the tension. They do not take compression or shear. They are purely designed to take the tension. The cables are formed basically by twisting the different fibers, the steel composite fibers, at different twisting, so that the load carrying capacity can be alleviated. They can be used as to support the suspended suspension roofs. They can be used in suspension bridges, trolley wheels, etc. So the self weight of the cable is taken as a negligible, because the comparative to the imposed load, the self weight is negligible. When used as these cables can also be used for the transmission lines that I also have mentioned. Um, for the design of a transmission line, their weight must be considered, because the transmission lines, they have a very lifespan, and the weight basically stimulates the design of a transmission towers. So it's important to take the weight of transmission lines while designing the towers. So cables subjected to the concentrated load. Here we have a cable which is subjected to P1 and P2. uh, there is basically three member elements of a cable, which is AB, BC and CD. So support A and D is elevated at different elevations. The support A and D is at different elevation, you can see that. And there was different span length L1, L2, L3, which constitute the total length of a span between A and D. So the free body diagram shows that it has hinge support at A, and hinge support at D. If we take a section at D point, then we will get to know that there are two reactions at each support. By taking the section at D point, we will have a AY and AX at support A, TC and TCD, which is a tangent force between the member in the member DC. Then we will apply the moment, sigma moment at point A equals 0, in order to obtain the tension at element CD. So we will apply the moment, and after the application of a moment, we will have one equation. Basically over here we have three unknowns, which is AY, AX and TCD. So for calculation of a three unknown, for determining the three unknown, we must have a equilibrium equations to solve this unknown. So we can take the sigma moment equals 0, sigma of x equals 0, sigma of y equals 0. By constituting by taking all these equilibrium equations and solving simultaneously, we can get the values of TCD and AY and AX. So we have a cable, we have a three span of a cable with a loading applied on it at B and C. So we have to calculate the tension in each segment. So what we will have to do is, first we will have to draw the section at some point. Let's say I will take the section at point D. the unknown forces at this stage would be A, Y, A, X and TCD that I have discussed earlier in previous example. Then we will take the sigma moment at point A, and sigma f of x equals 0, sigma f of y equals 0, and compute solve solve these three equations simultaneously to come up with the value of ay, ax and tcd. So if we take the moment sigma moment at a equals 0, here we have a tcd into the cost component multiplied by 2, which makes the moment counterclockwise moment at point A. Then we will multiply, we will take the horizontal component of TCD, that is TCD sine of theta into this horizontal distance. We will also take the moment values due to the applied force B and C at point 2 and 4 meters away from the two spot A. So 3 into 2 is a moment due to the force 3 kilonewton, and 8 into 4 is a clockwise moment generating the net. The convention we have taken as counterclockwise moment taken as a positive, while the clockwise moment are taken as negative. So we will have a TCD value equals 6.79. Then we will take the joint C. We have a TCD known. We will take the joint C. We will make the member force BC known. We will determine the member force in BC while taking the joint C. At this joint, we will take the sigma f of x equals 0, sigma f of y equals 0, and we will determine the TCB value, which is 4.82 kilonewton. So similarly, we will take the point D and solve point B. We will take the point B, and we have a known value of TCB tension in BC span of BC span, and which helps to determine the tension in BA member. Similarly, we will do the sigma f of x equals 0, sigma f of y equals 0. Now we have a TBA equals to 6.90. So in this way we will determine the tension in the string. In this way we will determine the tension in the tension elements or cables. So if we consider the cable subjected to the distributed load, we can take the example of our distributed load which is acting at its centroid point. Now T naught is a tension, which is a horizontal component, and T is basically the tension, which is a tangential component upon the cable. And there is a W. W is a resultant of a whole uniformly distributed load acting upon the cable. So if we form the triangle or a triangular shape, by resolving these three forces, we can make the W, T naught and T, which is separated by a theta. So we can T cos of theta can be taken as T naught. If we sum sigma f of x equals 0, then we will solve it as a T cos of theta equals T naught, which is horizontal force, which is basically the horizontal force applied, Fh, which must be constant. T sine of theta would be equal to W, which is a component, which is a resultant of distributed load. Then we will we will take the ratio of these two components to form the tan of theta, so that we have a W divided by T naught. W is resultant and T naught is horizontal component. Similarly, we have a truss. Similarly, we have a cable upon which the uniformly distributed load is laid. we'll have to calculate the tension within the cable member. So what we do is, first we have to calculate the W naught, which is the resultant force divided by horizontal distance, which is basically uniformly distributed load. We'll take the section. We'll take the section at this point. Here's a chunk of a section upon which the UDL is distributed, and x is some distance at which the section is taken, and we have a W naught x, which is a resultant force acting as a result of a UDL at this section. Basically, W naught is a intensity of a UDL per feet per unit distance multiplied by that x distance makes a resultant of force. So here's the x over 2 distance, which is the half of the distance of this section. We'll have a T naught, which is a horizontal component. T, it's a tension within the string upon which the UDL is distributed. We have a theta at which the tension is applied, or a angle theta at which the tangent can be drawn. So if we draw the resultant component, if we draw the triangle, so to solve the tension within the string, so what we will make is T naught, which is the base, W naught x, which is the perpendicular, and T, which is hypotenuse. In this way we can take the tangent to resolve its in its component, which is W naught x is perpendicular and T naught is its base. So we have a tan of theta equals W naught x divided by T naught, and we will take the differential upon the tan of theta, so that we can solve it. So we have taken the differential, and the constant in this case would be 0. We'll assume that the constant C1 is 0, and afterwards we will determine the T naught value, which is horizontal component. T naught in terms of intensity and horizontal distance, and y is basically the vertical distance. So T naught at distance x equals L, or at extreme support, the T naught would be T max. So we can say that by resolving by transforming this triangle into the section taken at point B. So we have a W naught L because x distance equals L. Then we have a tension which is equals to the maximum value T max. Then T max can be written as in its component T naught square plus W naught L square. And from the solved example we can see that T cos of theta, if we take the differential of a T cos theta, it would be equals to 0. If we take the differential of T sin theta, it would be the intensity of that load. If we take the tangent, then we must have to differentiate dy over dx, which is a slope. So we also have determined that the maximum value of T, the T is basically the T naught is basically the horizontal component, which at point 0, which can be taken as fh. So T cos of theta can be equated to fh, horizontal component, and on the other hand T sin theta can be equated as W naught x, which is basically the resultant of UDL distributed over the length, uniform length, unit length. So if we take the tan of theta dy over dx, we will able to get the W naught x over fh. So here comes an equation. If we differentiate dy, if we integrate this equation, we will have W naught x square divided by 2 fh, and taking y equals 0 and x equals 0, and we will have a f of h, which is a horizontal component of force, which can be calculated as w naught L square over 2h. So fh can be computed by resolving, by making the subject fh in this equation. You can get the w naught, which is an intensity, L square, which is the length, and 2h, which is the difference between the supports. So substituting this value into this equation 5.7, will have a y equals to h over L square into x square. The maximum tension occurs when the theta is the maximum at x equals L. So the equations 5.4 and 5.5 would be like T max. We will compute the T max value over here. Then it would be W naught L. We will compute the value of FH and W naught L square. If we compute the value of FH in this equation, which is 5.8, will have a T max value, because the maximum value is where when the theta is maximum, so it's around the support. So if we take the value of x equals L, means it will have reach the other support, which is the B support. Then we will have a maximum value of a tension. So we can apply the formula that we have derived earlier to solve this example. We have a cable shown in the figure. We have a uniformly distributed load of 12 kN per meter, and we have to determine the tension at point A, B and C. So we will divide this cable into two components, or two section components, which is BC and AB. So we will draw the section over here at point B. We have an intensity of 12 kN per meter, and we have so we have a differential support equals to 12 minus 6, which is 6 feet between the difference between the supports A and C. We'll calculate the TC, which is acting at theta C, and we'll calculate TA, which is acting at theta A. We have a total span of 30 meters. We'll assume that it's L dash, L prime. The other dimension will be 30 minus L prime. So we'll take the section over from here and from here. We'll take the section from point B and superimpose the values. We will have a TC and TAB after resolving and superposing these two sections. So section BC is, we have a 12 kilonewton meter force acting in the form of a UDL. So what we'll do is we just calculate TC and T naught. T naught is a horizontal component, TC is a tension at C point. We'll take the section at distance x1, and we'll draw the resultant of a UDL, which is acting at the midspan, which is 12 into L prime, which is the resultant of that UDL. Then if we resolve the component of this section that we have discussed earlier in the previous symbolic example, then we will able to determine the value of TC. So T naught is a horizontal force over here, TC is a tension at C point, and 12 L dash is basically the component of that resultant force. It would be computed as this. So by tan of theta, by finding the tan of theta, we can compute as 12 x1 divided by T naught from the tan of theta. If we derive the if we integrate this equation with respect to y with respect to x, then we will come to know that it will form a value of 12 into x1 over t naught, where the limit approaches to 0 to L dash. On the other hand, we have a x1 which is a differential or a slope difference, or we have a differential of y dash equals 6 meters. So we can what we can do is we can calculate the value of t naught from this equation by computing the value of x. So as we know that the maximum value approaches when there is a maximum maximum value of a slope. So a maximum value of a slope approaches at the support. So if we compute the x equals to uh, if we compute t naught as a L dash square in this equation, uh, if we compute the x1 as a whole L prime, if we compute the x1 as a L prime, then we will get the value of t naught as L dash square. So the tension would be equals to the square of horizontal distance. Then it's come to the other section, that is AB. We will try to solve it in a similar manner that we have solved the previous section. So what we do is it's a T naught and it's a T naught which is the component which is formed in a later section is a horizontal. 12 into 30 minus L is a component of a UDL. TA is a tension at support, tension in the string near the support A, which is acting at theta A. We will resolve it into a triangular component. 12 into 30 minus L is or the vertical component of force UDL applying. T naught is the horizontal component. TA is a tension near the string, and it's separated by theta A. So we can take the tan of theta, which is 12 into x, 12 into x2. On the other hand, in this we have a x2 equals to 30 minus L dash. We can differentiate it. If we differentiate it, limits between the 0 to 30 minus L, we'll get the value of T naught. We'll get the value of T naught. If we compute the y equals to 12, the T naught would be computed from this equation. Now we have a value. Now we have a T naught and L dash, which are two variables and two equations. We can solve this example by simultaneously solving these equations. So here are two equations. First one is T naught L dash square, which comes from the BC component, BC section, and this equation E1 equals to 30 minus L dash square divided by 2 T naught, which comes out from section AB. You can solve it simultaneously. You can compute simultaneously to result the L dash and T naught. Now we have a T naught equals to 150 kilonewtons, which is basically the horizontal force acting, which is TB at point B, and we have a L dash of 12.43 meters. So we can calculate the TC from this equation as well, by this triangle as well. TC would be equals to T naught square plus 12 L dash square whole square root. We'll compute the value of T naught and L dash. Will have a value tension near support C of 214.75 kilonewton. Similarly, we can calculate the TA. Here comes the value of TA. So here comes the end of this lecture, in which we have discussed in this lecture we have solved the cable elements on which the point load was applied, And in other example, we have also solved the uniformly distributed load over the cable elements, and we have resolved it to find the maximum value of a tension within the cable by this method. I hope you have learned a lot from this video. Thank you so much for watching. Allah Hafiz.